Hello there. Today we're looking at involution, inverting the inherence of convolution for visual recognition by a number of researchers of the Hong Kong University of Science and Technology, ByteDance AI Lab, and Peking University. In this paper, on a high level, the researchers try to replace the good old convolution operator in CNNs by this new thing called an involution. In its essence, involution is about halfway between a convolution and a self-attention kind of operation. And it turns out that with some clever weight-sharing scheme, you can achieve very good performance compared to CNNs and self-attention networks, while keeping the number of parameters and the computational cost relatively low. This, I think, is very much worth trying for anyone who does not operate on extremely large-scale problems. So we'll get into that a bit more when we go into the experiments, but for now, let's go through the paper, through what involution is, what it does, how it's different, and yeah. So if you like this, don't hesitate to share it out. It would help a lot. We're on the road to 100K subscribers, and with every subscriber, I get a subscriber. I stole that joke. So they say here in the abstract, convolution has been the core ingredient of modern neural networks, triggering the surge of deep learning in vision, which, correct, AlexNet, ResNet, etc. Convolution, even though transformers are slowly taking over computer vision, convolutions are still very, very much used. And if you're not on a super large scale problem, a convolutional neural network is still very probably the best way to go if you have a computer vision problem. They say we rethink the inherent principles of standard convolution for vision tasks, specifically spatial agnostic and channel specific. Instead, we present a novel atomic operation for deep neural networks by inverting the aforementioned design principles of convolution, coined an involution. Okay. And they say we additionally demystify the recent popular self-attention operator and subsume it into our involution family as an overcomplicated instantiation. So a lot of statements in this paper are true, especially further down. A lot of the experiments are really cool, but it is a bit of an overstatement what they say right here. So their claim is that if you have a convolution, what you do something that's spatial agnostic and channel specific, which means that in a convolutional neural network, when you have an image, let's say, with a bunch of pixels, these are now true pixels, not patches, and you run a convolutional layer over it, you run a convolutional kernel over it, you put the center of the kernel at some pixel, so the kernel will be something like a 3x3 kernel. You put that on the center here, so it overlaps here. You multiply element-wise, and then you aggregate. And you can do that in multiple channels, but essentially you do that. And then after you've done that, you move the kernel one, let's say, to the right. You shift it. So the center is here. You do the same thing again. And you shift it, you do the same thing again. So it's spatial agnostic because it repeats the same computation over and over and over across the image. And it doesn't care where the computation is, right? It does the same computation. And that is a selling point of convolutional neural networks. They are translation invariant. It's a form of weight sharing, right? You share the weights across the locations, and therefore you don't really care where stuff is in the image. The CNN will be able to recognize it just as well, and you don't need to learn over and over and over the same principle just because it's in different parts of the image. So this is spatial agnostic. What does channel specific mean? For that we have to go into the multiple channels realm. So if your image has multiple channels, let's say I'm going to draw a new image right here with a bunch of pixels, and it has multiple channels. That means you can imagine it sort of as a 3D tensor here, where each pixel is a column, and every column is a vector of a certain dimensionality. I mean, so the original image has, of course, 3 channels, which is red, green, and blue. But if you have intermediate representations, these channels can grow to sizes of hundreds of channels. And the point of the channels is every entry here is a number, and every number can sort of capture one aspect of what's described in that particular pixel, right? So maybe the first channel is there a corner? The second one, is there an edge? The third one, was it originally a blue pixel? The fourth one, is there probably a cat here? And so on. So these are like the different features in the channels. And a convolution operator is channel specific. That means if you have the kernel, now convolutional kernels aren't as easy as I drew them. They're in fact 4-dimensional tensors. So that is, they are 4-dimensional tensors, which makes it a little bit complicated for me to draw, honestly. However, if you can imagine that you have one kernel like so, okay, that has the same amount of channels as your image. Okay, so now you can still do the same operation, right? You can overlay your kernel on a part of the image. You can overlay it like so, and that's in the back. And then you can do element-wise multiplication, and then you do a sum. You sum it all up, right? After you do this operation, you do a big sum over all the elements of whatever your kernel multiplied with your image, and that gives you one number. Okay? You do an all reduce. One number gives you one number. And so you do this. So this is one kernel, but you have another one right here. Yeah, like this, and you do the same thing, and that gives you also one number. And you have another kernel. I think you get the idea. You have another kernel here. So you have many of those kernels per layer. When you actually, if you've never looked at, how the weights look when you instantiate these layers in a deep learning framework, encourage you to do so, right? A convolutional layer will have weights that are of the size by input channels by output channels. So it's a 4D tensor, and the orange part here, is just one of those subtensors. In fact, you have as many as you have output channels. And that gives you, of course, when you then go over all of these, that gives you the next layer. So that becomes in the next layer. So this is the next layer representation, right? At the point where you overlaid the kernel in the last thing, that will become this column right here. Okay, so you have the orange thing in the first, the blue thing in the second channel, the green thing in the third channel, and so on. Hope this is relatively clear. So you have, in fact, one convolutional kernel per output channel, okay? So if you call the orange thing here a convolutional kernel, then you have one kernel per output channel. And that means it's channel specific. Okay. So this is a conscious choice, and it makes sense when you think about it, because each output channel means something different, right? If my output channel means, is there a cat at this particular location, then I might want to aggregate the last layer's representation differently Then if my output channel says, well, is this part of the sky, or is there a corner here or something like this? So I want to aggregate the weights differently. That's why I have to have a different set of weights here, here, and here, because they mean different things. So it's spatial agnostic because it does the same computation at every location. It's channel specific because it does a different computation at each channel, even though it does it for all the locations equally. All right, so now we're prepared to invert that. So involution promises we invert this. What we want to do is something spatial specific and channel agnostic. Okay, so the first thing here is the channel agnostic. If you've seen my last video about MLP mixer, this is very much the same idea. And the idea is just of, hey, why do we have different things here? Why do we have different computations? Can't we just, apply the same principle we apply to the spatial thing, where we say, we just slide the same computation over the image, and that is generally fine. That's weight sharing. It's actually good. Why don't we just do this here? Why don't we aggregate the information in the same way for all the different channels? And yeah, so you can do that. You can just have one kernel. So instead of having number of output channels, many kernel, so the involution will come up with simply one kernel that it shares across all of the channels. They have a little picture down here, and just look at the at the last step right here. So here, wow, sorry, I crossed that out. Here, this is the kernel that they have. Sorry, it's not even by number of channels. It's actually, you just flatten this thing, right? So it's a k by k by 1 kernel, and you simply put that over a location in the image, and then you share the computation across. So the image here, given that this is all in the same colors, it means that you just multiply, you broadcast, that's the word I was looking for. You broadcast the operation across the channels, and then you aggregate after that. So you can see what involution does is broadcast and then not reduce, right? You don't reduce at the end to a single number, but you keep the channels, the channels as they are. That's why you only need a k by 1, because you don't have the different computation for each output channel, and you don't reduce across the input channels. So you get away with a lot less parameters. So that's even wrong here. Just a k by k kernel. Now, that's one part. The other part is, why don't we do something that's spatial specific? Spatial specific. And now remember what spatial agnostic was. Spatial agnostic was we slide the same kernel across the image. What they're saying in first instance, they're saying things like, or they said something, don't know where it was in the picture, but they say, well, what we could do is, if we have an image, right? If we have an image, big image, and we do something spatial specific, what that means is we could have a kernel that's just as big as the image, right? Then no more sliding across it. It's simply you multiply those things together, you broadcast it across these channels of the image, and there you go, right? that's it. Also, something that MLP mixer does, right? They just say, whatever, we don't do slidey anymore. We simply, I mean, they do weight sharing, but essentially, you're trying to get rid of this sliding over. You have different weight for each location. And that means that the computation actually differs from where stuff is in the image. And we know that that is somewhat important because usually the sky is up and, objects in these natural images that humans take might be more in the middle than anywhere else, and text goes from left to right. And so it's not all super translation and location invariant. So it makes sense to have weights that are different for each position. But then they run into a problem. They say, we couldn't do that very well because now we can't just input pictures of different resolutions, right? That's one problem. I think the other problem is that this might not work too well. So they come up with a different thing. They say, can't we make a compromise? And they don't call it a compromise. They call it something different. But they say, look, can we come up with a scheme where we can retain a kernel that's approximately this size, like a small kernel, but it is different for each location. So we still do the sort of classic convolution way of doing things in that we do these local aggregations across neighboring pixels. However, the kernel that we use here is different from the kernel that we use here. And that's different from the kernel that we use here. So how could you make a computation where the kernel is always different? You do that by coming up with the kernel in a dynamic way. So the authors here, they say, okay, if, let's say we're at this pixel right here, we care about this neighborhood. How can we come up on the fly with a kernel for this particular pixel? And their answer is, well, let's just generate it from the pixel. So this is the full involution diagram. We've now arrived at this. So they are at this neighborhood, which is outlined here in this black scaffolding grid thing. The center pixel is the red pixel here, this one. And they say, we look at that pixel and all its channels. And we use that pixel and only that pixel. So not the neighborhood, we use that pixel to come up with the kernel. So they have a computation here, which of course is going to be a small neural network. So this is a two-layer neural network that comes up with the kernel. You see this is simply here is just a reshape. So you compute the kernel across the neighborhood from the pixel itself. Okay? And that means that every single pixel here, unless it's the exact same pixel, so the exact same color in the first layer, or the exact same representation in the intermediate layers, every single location gets its own kernel for the convolution. The computation I've already told you is a small neural network. Specifically, it's sort of a bottleneck neural network. So it takes the pixel representation as a vector, sort of bottlenecks it. There is a nonlinearity here, and then it expands it again to the size of the actual kernel. Okay, and then you use that kernel and you broadcast it instead of having one kernel per input channel. And then you multiply, and then you don't reduce by across the input channels. Okay, sorry. Yeah, I said, and that alleviates you from having to have multiple kernels, one for each output channel. Okay, now this is the whole involution pipeline. I would say there are multiple different concepts here. So this coming up with the kernel on the fly is one concept. And then this broadcasting scheme is an entirely different concept. You could do both independently of each other, and they do them together, they do ablations further down. but it's sort of two new things in one. Now, the first thing here is very much, you might think of attention mechanism as you look at that, because it's a form of fast weights, right? So the weights of the computation, they are computed on the fly from the data itself. And that is exactly what an attention mechanism does. However, here you do it in a slightly different way. And they say that they have a discussion about attention right here. So they say, there are a bunch of differences. So in attention, what you'd have is you don't only compute your weights from the actual location where you are. Even in local self-attention, you actually compute your weights from more than just the pixel where you are. You compute it from the entire region you care about. So that's the first thing. And then the second thing is, in the self-attention, you have the queries and the keys, right? So you have your data, your neighborhood, let's say, and each of those things produces a query and a key, right? Query, and I'm going to write the key up here. Everyone produces a query and a key. And then you do this sort of quadratic thing in order to determine how you should aggregate your information. Not in involution. In involution, you simply don't produce keys. You only produce queries, if you will, or only keys, however you want to look at it. And then you don't do the quadratic thing. Rather, you immediately interpret this as sort of the weights of aggregation. You can write this, and they say that you can interpret this as the positional encodings already being present in these weights, because it's now specific to a position, whereas in the attention literature, you'd have to supply positional encodings. So in order for the algorithm to know, that this is a different thing, that this here is a different thing from this thing here, you need to supply it with positional encodings. Not here, because the individual channels of this thing immediately refer to different positions right here. So this neural network is very aware what position is where relative to the pixel you're considering. So they say the success of involution explains in part why other people had lots of success with leaving away the keys and only using positional encodings together with the query. And if I'm not mistaken, this is a thing, I think you could frame the lambda networks into this category where at some point, they never do this attention. However, they rely heavily on positional encodings. However, you can learn those ahead of time, right? Or statically. All right, that's enough of so this is the connection to attention. The connection to attention is the weights are constructed on the fly. However, here there's no quadratic interaction. There is no softmax and so on. It's just you construct the weights from the pixel in the center. Therefore, it's less powerful. To frame attention as it's a more complicated instantiation of our idea, that's a bit out there. The authors here, they say, well, attention is just a more complicated thing of our thing. Nah. And the second thing I worry a bit about is they say, well, this is position specific or location specific, right? They started out with saying convolution is spatial agnostic. We want to do something spatial specific. This here is also spatial agnostic. If you get the same pixel at different locations in the image, this thing will produce the same weights and the computation will be the same. In fact, you do this entire computation right here. That is a spatially agnostic computation. It's just, so the difference here is the same difference that you have between slow weights and fast weights, where you simply construct the weights of the actual computation on the fly. However, the way you construct these weights, it remains position agnostic. So that's the first thing. And the second thing, yeah, the weight sharing, I feel, is a bit of an independent thing. Now, I get it that the two work well together, but the broadcasting and weight sharing thing across the channels, it's almost a separate, much simpler mention, and it's a bit related to. So if you have a depth separated convolution and you simply share the weights across that, that's about what it boils down to. So what does that give us? In fact, it gives us a lot. In this paper, they do experiments and they compare against, for example, so against ResNets and other networks with similar number of parameters. And I like these experiments here in that you can see they always make sure that they have the lowest number of parameters among the things they compare with, right? Yet they show that they still beat these models. They still are better than the models they compare to. So they do that, and specifically, I guess they compare to ResNet with the same number of layers, standalone ResNet. This I think is self-attention. I think here's the axial ResNet. So that has a little bit less parameters, interestingly enough. But yeah, so you can see that this outperforms on these tasks right here. So this is ImageNet. They also have different things such as this segmentation task. I think they have a picture down here. This segmentation task where they perform better. So here, I think this is the baseline, and you can see the involution network. It does a better job at this kind of things, which is believable. I think the effect that you see right here, the fact that they are better in this number is really cool. And it's probably a bit, due to the fact that they do this on-the-fly computation of weights, which is a more powerful idea than the static weights of a convolution. And then the lower number of parameters, I think, is more a result of their weight sharing scheme, right? They tout here how that they is on par with ResNet 101 regarding the top one recognition accuracy, while saving 65% of storage and computation. So I think that the saving of computation is more due to the weight sharing mechanism. And I think they've just here selected tasks, and they might be important tasks, but I think it was just the case that in these tasks, whether or not you share the weights probably doesn't matter, doesn't hit you as hard, or is even beneficial if you don't have enough data. And therefore, that's why they have less parameters, right? So what you can also observe here is that differences, they get continuously smaller as you move up the scale of network. Now, this is all on the same data set, but it would be interesting to see how this performs on really large scale, because my intuition is that as you go larger and larger in scale, this approach is gonna top out and lose out to the more general architectures like attention and whatever MLPs. Apparently, it's a clown world now. But in these regimes, and I would argue these are the regimes where a lot of practitioners care about, these and actually smaller regimes, so not many people are in the super high data regime, this seems to perform reasonably well, right? So you can see right here, the curves here, when you compare compute to accuracy, is very favorable. Again, especially if you're in like this region here, if you're in the low resource region, it might be something that you want to try out. It remains to be seen how well this is pre-trainable and fine-tunable and so on, but it's something you might want to try. Also, if you try to only use sort of parts of it. It would be interesting to see, if we still do convolution, but we do this sort of weight sharing scheme, this broadcasting scheme. And yeah, they also have a notion of grouping. in the channels. So as as the attention mechanism has it. So here they say it. However, sharing a single kernel across all channels obviously underperforms in accuracy. Considering channel redundancy of involution kernels, as long as setting the channels shared in a group to an acceptable range, the channel agnostic behavior will not only preserve the performance, but also reduce the parameter count and computational cost. This will also permit the larger kernel size under the same budget. So it's sort of the same reasoning as people introducing groups or different heads in multi-head attention. So try all of this stuff out. I think it's worth it. The code is available. Code is available right here. And I'll also put a link to that. And that was it from me for this paper. I wish you a very pleasant whatever the day of the week is, and bye-bye.